Okay, so now we'll talk about GPU programming again. I think the last time we had a strange experience. I don't know, who of you read my long Piazza post about this? This race condition among our GPU threads. Okay, none. All right. In that case, maybe I should just review that first. So let's see. Okay, so we were working on a kernel it looked something like this. Yeah. And the plan was we were going to try to figure out something about sort of the order in which things execute on the GPU, what all these threads are up to, and so on. And in particular, we're going to work with this local variables a little bit. So here we have a local variable being a variable that belongs to the work group. Right? Every work group has its own copy of this local variable, or at least that was my impression. Right? But then it turned out during class that, well, actually there seems to be some interference between work groups and what's going on here. So let's see if we can get this to run again. I thought this was a very good, kind of an embarrassing but very good experience. So let's go to lines. I guess everyone had a good Thanksgiving then. You didn't end up reading my long post on Piazza. I had a good one too. Okay, so we were doing this thing. Here's this program. We're running lots and lots of clients. Let's see. We have a work group of size 256. So that means there will be 256 work items within one work group. And we had a relatively large problem set, so lots of work groups as well. So every one of these threads just sets this work group number to 0, work group count to 0, if it's, because we need to initialize it. So if we are item 0 in this work group, we set the work group count to 0, and then we all increment the count, and then we report the work group count to the CPU through this result array. So basically, we want to see, like, for each ID, what count did they all observe? All these work items, what count do they observe? Okay, so the output was something like this. And then we wanted to, we were looking at the third column just to see what different work counts are we seeing. Okay, so that was it. So we were observing that, most fibers, most work items are seeing a count of 128, right? Or actually, there's all sorts of different counts here. 64 is a common one, 96 was a common one. So there's all sorts, right? But the theory was that this work group variable is local, and every work group is of size 256, right? Let's see. Work group size is 256. And so we ought to be seeing, well, at least numbers between 0 and 256. There's no way that we can go up above 256 because the work group size is 256. So that was the mystery. And I came up with this, unfortunately, completely wrong conclusion in class that this local, because it sits in local memory to the streaming multiprocessor. It's actually shared between whatever work groups are running on the streaming multiprocessor at the moment. And that is nonsense. I thought about this over Thanksgiving, and I couldn't figure out how you would possibly program with that kind of variable. What would be the point when it's shared between these supposedly independent threads? I couldn't reconcile that. So I had to go back and experiment a little bit with it. And it turns out that that wasn't the case at all. The problem was, well, kind of, sort of. So if you have multiple work groups running at the same time, they each have their own separate variable. But there's lots of work groups running on this in this problem, in this program. So at some point, one work group finishes, retires, releases its memory. Another work group gets scheduled. It will use the same memory. So they're not running at the same time using the same variable. But later on, when you come in, you will probably be allocated the same memory a previous work group was using before. And that's fine. There's no race conditions there. The problem is if you have an uninitialized variable. And that brings us to what was actually going on. So here we're saying, oh, if we're local group, if we're the local ID 0, we initialize it to 0. And that should be fine, right? The 0th item initializes the work group count. Unfortunately, because we have now 256 items executing in parallel one way or another, certainly 32 were executing in parallel on one of those chunks in the streaming processor, right? That one warp of 32 runs at the same time if there are no branches. But also across different chunks, we can be running 4 different warps at the same time within the streaming multiprocessor. So what happened was, we have one warp 1, which includes this local ID of 0. That kind of gets hung up here for a little while. So only one of these threads, or one of these work items, gets scheduled to do this work. The other ones have to wait. They're not continuing. On another part of the streaming multiprocessor, we're running another warp of 32. They don't worry about this, right? They have nothing to do with this. They just continue on. So they will start adding to an uninitialized variable before the variable gets initialized. There's no ordering between the various work items. So the solution then, we have to make sure that the variable is initialized before we start working with it. So a barrier will take care of that. See how that changes the result. Okay, so it got better, right? It's not quite there. Why are we seeing different results here? Any thoughts? They're not all 256. Why isn't the work group count? We're doing all this adding atomically and all. We're not really losing, but we're between 32 and 256. How do we get these different counts for different work items? Run this a couple more times. So the result we're reporting here That's what the current warp is observing. Yes, there are atomic adds, but here we're reading. We're not taking the result from the atomic add. In that case, we would actually get, we should do that too. In that case, we would get every one a different value, between 0 and 256. In this case, the warp is running an atomic add, and then we're reading after. So we'll see all these 32 adds happen at the same time, right? But we're not necessarily seeing all the adds of all the other warps within this work group. So we get increments of 32 automatically, and we'll see different counts in there. If we want to have them all be the same, then we need another barrier, so we know that everyone within this work group has finished doing the adding. Right. Or alternatively, if we actually want to see what every what every thread is observing individually, we'll have to capture it like that. I keep saying, oh, result is no good. So then it'll be all the values between 1 and 256, and of course 256 of each one of them, because in every work group there's only one atomic add for each such value. Okay, so this I think makes the semantics of the GPU execution a lot more clear. The local variables are very handy because sometimes you need some coordination within the work group. I think the work group, the choice of the work group size probably has something to do with these local variables too. Like, if you're multiplying arrays that are 32 wide or 50 wide, you might want to have a work group of size 50 because it makes sense, and then you have a local variable for that. In any case, local variables have two good things. One is they're local to the work group. The other one is they are local to the streaming multiprocessor, which means they are running really fast. So the latency is similar to an L1 load for the local variables, whereas global is similar to a DRAM load. So it'll be a 2 order of magnitude difference in access times. That's only if you actually use the memory multiple times, though. There's no point in kind of loading from the global memory to a local variable and then accessing the local variable once. You've already incurred the cost of loading from global, so that doesn't give you anything. All right, so I wanted to actually before I move on, any questions on the semantics of execution? Any further questions on that? All right, so there's the global ID, which is a unique number for every work item. And then we have the local ID, which is the index within the work group. We have the group ID, which is, you take the global space, say it's a million, and the group size is 1,000, then there will be 1,000 different group IDs. Right? So there's also group size that we can get. In terms of synchronization, the only thing we have is barriers, and they only work within the work group. It's worse than that. Every work item has to hit the barrier. So you can't have a barrier within an if condition because, well, the barrier is going to wait until you have size of the work group that hit the barrier. So then you'll basically it'll just hang. So this makes things kind of difficult. We don't have any safe shared memory access whatsoever. Right? Shared memory, the best we have is the locals. They're shared within the work group. There's no shared memory for the DRAM. Like no safe, no atomics. Oh, actually, there's atomic add, but there's no synchronization between for global memory. There's still atomic adds, and there's a couple more atomic instructions you can use. Okay, so the other program I wanted to look at is very similar. Let's see. Let's see. Did I open? Oh, I got the wrong program. There it is. Okay. So here's the deal. We have an array of problem size integers. And now we're getting larger. We want to do this on a GPU, probably because this is a very large problem, and so we think GPU programming might help us in some way. So the problem size right now is 100 million elements. And the job is to find the minimum value and its index. Right? And just to make this a little kind of easier to verify that we're actually doing the right thing, the program is generating random numbers, but in the end, I put in a negative number at index 18, and so as long as we find that one, we're okay. That's the kind of simple test. Okay, so I have this running on nodes without a GPU. Okay, so that's taking 170 million cycles. This is kilocycles there. So 170 million cycles with full optimization and with vectorization. And this is a, let me see. Yeah, this is the index min, right? So it could go faster if we had proper vectorization, but probably because we're looking for the index, probably it didn't actually do the vectorization. Okay, so now we want to try to come up with a way to compute a minimum on a GPU. It's not entirely obvious. It's easy on a single thread. You kind of run through, you start with one minimum, you run through to the end, and then you're done. Right? You have the minimum. But now we're going to run this on many threads, and we need to be using thousands at least. So what do we do? Well, I guess we could make 100 million items, work items, because there's 100 million elements. But then how do we get to a minimum? To do a minimum, we basically have to do a compare. Right? So I think 100 million items doesn't make any sense. There's no, we don't get any benefit from that. So maybe a good start would be to chunk up this problem space into a reasonable loop, say 32. So now we reduce the problem space by a factor of 32 in one fell swoop, right? So every work item now becomes a loop of 32 that we run through. So now we have at least a 32nd of the size. And we can maybe do it again. Okay, let me go to lines. So there's a little bit more infrastructure here on this one. I thought I'd explain how it's set up. Okay, so every work group has some number of items. It's unclear what size the work group should be. Right. Probably depends. In this problem setting, there isn't a natural workgroup size. It has more to do with the architecture. But we can try with a workgroup of 1024. That's nice. Then in that case, we will have not very many minimums in the end. So every workgroup computes a minimum. Every work item computes a minimum inside it. Right? So we do, in this case, it's set up to do 256. Every item computes a minimum of 256 elements. And then every workgroup has 1024 items in it, or threads if you want. And among those 1024 threads, we compute a minimum. So now it's 256,000 in one work group, right? 256,000 elements. And then finally, at the moment, this driver program here is printing out the minimum that was produced by each work group. So work group 0, so there's 400 times 256,000, that's the 100 million elements total. Okay, so this is what we're getting at the moment. Maybe we'll stick with those numbers for now. 1024 size work group and a chunk size of this, and we'll just try to make a minimum implementation first, and then we'll play with the sizes to see what's going on performance-wise. Right. So we know our local ID. This was just to kind of output a number. Right? You see here. For the result that we're putting out, that's in this dmin. So we have now 400 results that we're outputting, and every work item is just writing its ID into this. So we end up with the last work item's ID everywhere. Right? Every result is every work group result is the last work item's ID. So it's, looks like it's actually not quite. I guess there's no guarantee that we get that one ID. But we're going to get an ID within the work group at least. That's guaranteed. Okay. This runs really fast. We have some timing on it as well. So the kernel finishes. The execution of the whole kernel finishes in 124,000 cycles. And I guess that's okay. That's quite a lot of fibers to run. Not fibers, work items to run. Okay, so how do we get a minimum? Well, I suppose we'll need a for loop. Where should we start it? So we're going to do this, let's see, it's like this. Loop overall the whole chunk assigned to this item. Right, so we have our values coming in here. That's where we want to find the minimum. This work item is responsible for, what was the chunk size? 256 elements. And the chunk size is coming in here. So we need a minimum for this work item. Well, maybe if we draw it, we can kind of figure out how this is supposed to work. All right, so we have our 100 million elements, and that's all divided up into a bunch of work groups, right? 400 work groups, 400 of these, and within every work group there is 1,024 work items, 1,024 of these. So we basically need to sum up. Within here, there's, how many were there? 256, a chunk size. Okay. Chunks of 256 elements. What was it? Let's call them items, work items. So there's 1,024 work items of 256 elements, and there is, there we go. I hit the hide button somehow. No. And there is 400 work groups. 400 of those, 1,024 work items consisting of 256 elements. Okay, so inside of here there's 256 elements. And then of course there's, for every work item is its own one of these, right? So we have to start here somewhere and then add up or find the minimum throughout the chunk that is assigned to this work item. So our start, let's have is our ID, right? There was that is the global ID for the whole for this work item. But then we should space it out so that everyone operates on their own part of the space, and it's spaced out by chunk size. Right. So we start at our own chunk. And then we add up everything until start plus chunk size. We don't add them, we minimum them. I guess we can say like this. Right, and then if min is greater than okay, so now.
You have an extra underscore in the index.
Thank you. All right. So now we're running in parallel 400,000 work items at the same time, right? There's 400 work groups, and there's 1,024 items in each work group. So at the same time, we're running this loop for all of them. They're all starting at a different offset, and they're running through 256 of those elements sequentially. I think an important thing to understand about the GPU processor is that it's really dumb. Right? Each one of these processors here, for the work item, there's no speculative execution, there's no out of order execution. There's no, at least in most architectures, there's maybe, I think I saw somewhere there's one that has some superscalar where you can execute 2 instructions at the same time, right? An add and a move or something. But generally speaking, it's not even superscalar. It can run 1 instruction at a time. The compiler is okay. It's not all that, but at least it appears to not be all that. But it knows about constant propagation. It knows about dead expression elimination, like not running code that isn't necessary. It can all get pretty confusing because you don't get to see the assembly. There is something like assembly, but it's kind of a half assembly. It's actually assembled again once it makes it into the driver. It's all rather obscure. Okay, so So these are actually going to run sequentially and slowly. Right? Each one of these will be one. You can imagine what kind of assembly comes out, and it'll run one of those per cycle, and we're running at about a gigahertz. But because we're running up to 400,000 in parallel, it's not all that bad. Of course, it's not 400,000 on this particular GPU. It was it 384, I think. Yeah. Yeah. So there's 3 streaming multiprocessors. Each one can execute 4 warps at the same time. Each warp is 32 of these work items. So 128 per processor times 4, 384 hopefully. Yeah. Okay. So anyway, we can hope that to actually execute 384 of these loops in parallel. But in the end, we only get, we're stuck with 400,000 minimums, right? That's not exactly what we want. Let's just run it for now, see what it does. Okay, so looks like we're getting a bunch of minimums that are increasing at least. These are minimum indexes. So it's making some degree of sense. Within each work group, there was 400,000 elements, and these are spaced out by about 400,000. So we have a minimum. Actually, it's not a work group minimum yet, but at least these numbers are to some degree making sense. It's a minimum for an item within the work group. Okay, so now, how do we get the minimum across those 1,024 items within the work group? One thing we could do, of course, is export it all out. We have each item directly report its index. Now we're reporting some kind of bogus thing here. We're saying every item overwrites the group ID minimum. There's only 40 of those minimum, 400 of those minimums. So we get 1,024 overwrites of this thing all the time. It's really a bogus reporting, but we could make this much larger, right? We could make it 400,000 items, report that to the CPU, and then do a sequential minimum with the CPU for the rest. That's one way, but it seems a little lame. We still have an array of 400,000 results here. We should be able to reduce that further in the GPU. And as we'll find out, the main limitation for GPU processing tends to be the PCI bus. It's not that running this minimum takes so long. Well, it actually takes a little while. I think we saw it here. I had the number. It took 75 million cycles on the CPU. Right. But 75 million cycles for 100 million elements, that's fine. It's not even a cycle per element. To compute the min index, that's pretty nice. But it takes, the total execution time actually was here, 400 million cycles. So computing these minimums within the kernel, 76 million, the rest of it is upload time. Right? Moving the array to the GPU and then moving the results back. This is a small results array of 400 elements. Don't worry about it, but the big results, the big value array of 100 million elements, that's a big deal. And we can't fix that. So in principle, it's probably a bad idea already, right? Because we're only computing one minimum. We're doing this huge upload over a slowish link to compute one value, and we're out of there, right? So, but generally speaking, you upload a large problem set to the GPU memory, and then you work on it. Even if you just did it twice, it would be worth it, right? So now if you want to do a minimum and then a maximum, we would incur another cost like this for the maximum. That's great. And of course, you tend to do bigger computations within the GPU. In any case, let's not worry too much. Let's remember that the data upload is a big limitation, but let's not worry too much about that for now. Okay, so there are some GPUs that actually sit on main memory. So Intel, if you have an integrated GPU inside of your CPU, that uses the same main memory. And their upload isn't a concern. That could be a major benefit. I think AMD has that too for some of their integrated ones. Of course, you get a lot less chip area, so you don't get as many work items in parallel instead. Trade-offs. Okay, so coming back to this, we have 1,024 minimums. That's my minimum here, right, in this work item. Now, how do we get a minimum over the work group? Any ideas? Yeah?
You should wait for like putting a barrier so that every thing.
Okay. Do a local mem hence. I think that's very good. So now, at least they're done computing their own minimums. So now what?
And maybe one of those and make it compute the minimum.
But this is a local variable. It's only available to, and it's only one. Right? So we need to somehow refer to the minimums of the other work items in this group. So far, there's 1,024 of these mins, but they're only available to each work item. How do we communicate with our other work group members? This brings us back to the beginning of this recording. A local variable, right? We need a local array what's the work? Okay, that's the work group size. OpenCL is really unhappy about variable size memory allocations. So you can't say like this. It just doesn't work. The compiler will say, I don't allow that. Okay, but we know the workgroup size is at most 1,024. In fact, this chip doesn't support workgroups bigger than 1,024, it seems. I'm getting some weird error, which I figured. Okay, so now we have some mins, and so that means we can just write out the min here. Mins local ID equals min. Oh, maybe we should have a min indexes too. I should make up my mind. Is it underscore or not underscore? Okay, so now the barrier actually makes a lot more sense because we have these writes to local memory, and after the barrier is done, now we know for sure that all the mins are populated and all the min indexes are populated. Okay, so now what? Now you suggested that we could pick one, right? So we could say if, let's just start with that. It's not bad. And then we'd want to loop through them. I guess we have a min already. Okay. should be pretty much done. Then min equal min psi. Right, okay. So I think that's a complete solution. It's kind of ugly though, because we're going 1,000, oh actually, was it? Yeah, it's 1,024. We're going 1,000 times around on this one slow work item, right? So we should be able to do better, but let's see how that goes first. Min was at 18, yeah, we found the correct result. Not bad. Looks like it didn't really slow down. And I think the reason is that this array of 1024, well, it's not that big, right? It's not like the huge arrays that we've been dealing with 100 million elements. But what if we wanted to make it a little more parallel, you know, just because? So one suggestion might be to try to do it like, let's make it half the size first. Right? We have 1024. We can just like make half of the elements be the minimums of these and those. Like let's get the 512 smaller ones first, and then the 256 smaller ones, and so on. There's successive halvings. That means we'll only do 10 times that. So 10 times around the loop instead of 1,000 times around the loop. So then we need to know like how big we're starting at. Let's call the local size. I think that's the same as the 1024 here. Maybe we should do that instead. Oh, that's not allowed on this one. Okay, that's fine. Okay, so let's go like this. I guess we'll start at half. So, so now for each of the elements here, if sorry, not the elements, items, work items. So for each work item now, we have 1024 running, right? So if we're among the 512 smaller ones, then we can see like, is my minimum smaller than the other guy's minimum? And if it is, then we just take the other guys. So I'm going to go through until the size until we have only one element left, right? So now we have 512 elements working. If my local ID is smaller than size. Otherwise, we're not interested. Right. So now I'm already discarding half of the work items. Right. The top 512, the lower 512. We want to see, if min's local ID is smaller than min's maybe we'll do like that. And then I'll just reassign it. So in indexes. Right.
Tyler doesn't complain about adding within the, like when you're indexing.
Oh no, compiler doesn't worry about that. The compiler is only worried about memory allocations. And the reason, so the size of the memory allocation, they're the local ones. The reason for that is when it needs to schedule another work group, it needs to know how big is the memory allocation the work group wants. And so if it's static, that can be part of the binary. It just says like, oh, you schedule this kernel, it takes this much memory. But if it's dynamic based on whatever, then there's no way for it to know. And so it can't pack those kernels into the local memory. Right, so what's happening here now? So now, after this, the 512 lowest elements in this array have the smallest values of those 512 and those 512. So it's almost like vector programming here, right? We're doing these vectors of 512 at the same time, but we're writing it in sort of thread programming way. Of course, we run this, for sure we run 32 at the same time. That's what the warp kind of execution model does. So we know that we will run from here, we will run all of the warps that are less than 512, ID is less than 512. Of course, here it's not clear that every work item is going to execute this. But if it doesn't execute it, it just goes to the end. And if it does execute it, then we run them. So maybe half of them, on average, will be running 16 of these assignments in parallel, and 16 of them will just be waiting here for the rest of the work to catch up. Okay, and then we divide the size by 2. So now we have 256. And so we're running 256 work items in parallel, and they're picking the minimum of those, of the remaining, of those 512. And then so on, until there's nothing left. And so, in the end, I guess, in index says 0. Does it make any difference if we, maybe we should say this. I'm not sure if it makes any difference for performance, right? For semantics, it doesn't matter. We're making the same assignment over and over, but for performance, maybe it's better to just have the one. In the end, we're going from 1,024 times around the loop to 10 times around the loop. It's not a whole lot of cycles. Each loop was probably taking us, 10, 20 cycles. So we're talking 20,000 cycles difference at most. So that's going to be a little hard to see on the measurement here, because this is in megacycles, in kilocycles. So 76 million cycles, and we're saving 20,000. Probably wasn't a very interesting experiment, but I thought that at least the design is interesting. Okay, let's see if we get the right result still. Yeah, okay. So that went a little faster, but I think that's just noise. Yeah. Okay, let's quickly look at what we can do in terms of profiling. There isn't a lot. Right. At least for OpenCL, there's no profiling support whatsoever for inside of the kernel. So you don't get to sample like we do on a CPU. You sample and see where we were running. Basically, what we can do is we can see how long did it take to execute a kernel on the GPU. And that's what's happening here. Let's see. Make this a little bigger. Oh, actually, how did this run finally? 380,000 cycles. And what did we do on nodes? Did I lose it? Sorry. I'll get it again. $180 million cycles versus 380 million cycles. So in this case, it was a lot faster to do this with CPU, simply because, well, the CPU had to do all the copying anyway. Like, or actually, I'm not sure about that. It could be that the GPU does a DMA copy, but in any case, the copy over the PCI bus of all this memory was slower than the CPU blowing through it. It has faster memory access than the PCI bus does. But if we were to do another couple of little computations of this order, right, work on our data set more than just finding a minimum, looks like it took us 300 million cycles to get the data in. Right? So as long as we do twice the amount of work, like do this work a couple of times on the data set, now it's a win with the GPU already. Right, okay, so all we can do in terms of profiling, I did two types of time measurement. I'm using the normal RDT SCP, the read timestamp counter, P for processor. It reads out the processor number into dummy here. So that one is cycles spent on the CPU between the two times. It's not that the CPU used the time necessarily. It's just how long did it take in cycles. And then I use this thing. It's called get event profiling info, and the only thing you can do really is get the time to start and end an event. An event is things like this. So here I include the kernel, right? That's the kernel that's doing all the minimizing. At the end here, I asked it to write out sort of an event ID into this here, the CL event. This just identifies one of these things in the queue. Right? You can also say over here, you can say, oh, only run this after some other event is finished. So there's ways to enforce ordering between events within this GPU if you're running many different kernels. In this case, we were just remembering the event so that we can then ask about it in this here, command end, command start, to get the start and end times in nanoseconds from the GPU. So I guess that's handy because we can't measure it with RDT-SCP directly. We don't get those internal details on the GPU. We could only get sort of what's happening on the CPU with on-host measurements. Right, so in terms of trying to measure what's taking long, I think the best idea is to try to split a kernel up into pieces, comment things out, right? See how long did it take to run the first thing, like we did here with the loop through. So that took 76 million cycles. Then we add something, didn't add much. I think that's the best we can do in terms of getting measurements. And you can certainly split a kernel into multiple pieces and schedule several kernels back to back and then measure each one of those kernels individually. Right, we have a couple minutes. I wanted to try something here. So, for example, why don't we go with a workgroup size of 1? So now there's no concurrency within. In fact, I don't know if that will even run, but let's try it. It should go slow, because we don't get, at least we would want 32, I think, so we can fill a warp, right? Let's see if this runs. There may be some allocation problems. Oh, yeah, there's also a whole lot of workgroups. Yeah, okay, so that's good. So it took us 500,000 cycles to run the kernel. This printing happens after. There's a lot more workgroups, of course, right? Because every workgroup only has one chunk, 256 elements inside it. Let's try something different. Let's go with 32. So now we get the parallelism of the warps, and because the scheduler will run many work groups independently, it seems like we got most of the benefit there. Now, I think there's some benefit to having a little bigger. Let's see. But at some point, this coordination between within the work group doesn't really give you that much. Yeah. So we're getting smaller number of minimums coming out, right? That's good. That's a nice advantage of having the larger work groups. I wanted to see one more thing. Let's try this, get rid of this chunk size. So now we don't have this initial loop. So now there's every one of these work items is only doing one piece, right? It's computing its own minimum. But then because we have so now we actually have a really clever, I think. Actually, let's see here. Yeah. It took longer in total, and I think that's because now we're uploading or returning 102,000 elements, right? 102,000 workgroup minimums to the CPU. So there's some trade-off there.
You also got the wrong answer, right?
Oh. Yes. Good eye. Okay. Well, we're also out of time. But that's interesting. Why would that be? I'll look into it. Anyway, yeah, I'll see you on Thursday. I haven't posted a homework. Shall we do another homework? What do you think?
No.
How many yeses? Okay. No more.